Hi, today we're going to talk about network protocols and communications. Network protocols and standards make network communications easier. First of all, we have rules of communication. All communication methods have three elements in common. First, the message source or sender. Second, the destination or receiver of the message. And third, the channel, a transmission medium of the message. Rules or protocols must be followed in order for the message to be successfully delivered and understood. Common computer protocols include message encoding, message formatting and encapsulation, message size, message timing, and message delivery options. The message encoding is the language that the message source and the message destination must understand. The message source has an encoder of the signal and it sends it to the message destination. Here the message destination decodes the signal and then therefore it can understand what the original message said. The message formatting and encapsulation means that each computer message is encapsulated in a specific format called a frame. Therefore before it is sent over the network. The format and contents of a frame are determined by the type of message being sent and the channel over which it is communicated. Messages that are not correctly formatted are not successfully delivered to or processed by the destination host. The message size exists because when a long message is sent from one host to another over a network, it is necessary to break the message into smaller pieces. The message restrictions of frames require the source host to break a long message into individual pieces that meet both the minimum and the maximum size requirements. This is known as segmenting. Each segment is encapsulated in a separate frame with the address information and is sent over the network. At the receiving host, the messages are de-encapsulated and put back together to a process and interpreted. The message timing exists because both the sender and the receiver need to know when to start sending the message, or if it's good to send the message. The access method determines when someone is able to send a message. Hosts on the network need to know when to begin sending messages and how to respond when errors occur. The flow control is how much information can be sent and the speed that it can be delivered. Source and destination hosts use flow control to negotiate correct timing for successful communication. And finally, the response timeout. Hosts have rules that specify how long to wait for responses and what action to take if a response timeout occurs. We have three types of message delivery options. The unicast, we can see it here, is one-to-one delivery. There's only a single destination for the message. Then we have the multicast delivery. It's one-to-many. The delivery of the same message through a group of host destinations simultaneously. Do not confuse with broadcast. Broadcast is one-to-all delivery. All hosts have to receive the message, and hosts have requirements for an acknowledged versus unacknowledged message, because in this case, the sender needs to be sure that the message is delivered successfully to the destination. A protocol suite is a group of interrelated protocols necessary to perform a communication function. Protocol suites are implemented by host and networking devices in software, hardware, or both. Here we have an example. The interaction between a web server and a web client uses a number of protocols and standards in the process of exchanging information between them. The different protocols work together to ensure that the messages are received and understood by both parties. Examples of these protocols are the application protocol. In this example would be the hypertext transfer protocol. The transport protocol in this example would be the transmission control protocol. The internet protocol, IP, and the network access protocol, in this case the Ethernet. The protocols IP, HTTP, and DHCP are all part of the Internet Protocol Suite known as Transmission Control Protocol IP, or TCP/IP. This protocol suite is an open standard, meaning these protocols are freely available to the public, and any vendor is able to implement these protocols on their hardware or in their software. There are some other protocols that are called proprietary. It means that one company or vendor controls the definition of the protocol and how it works. The TCP/IP protocol suite includes dozens of protocols. The TCP/IP protocol suite is implemented as a TCP/IP stack on both the sending and the receiving host to provide end-to-end delivery of applications over a network. The complete communication process consists on 1. The web server's hypertext markup language HTML page is the data to be sent. Then, the application protocol HTTP header is added to the front of the HTML data. The header contains various information, including the HTTP version the server is using and a status code indicating it has information for the web client. The third step is the HTTP application layer protocol delivers the HTML formatted web page data to the transport layer. The TCP transport layer protocol is used to manage the individual conversation between the web server and the web client. Then, the next step is the IP information is added to the front of the TCP IP information. The IP assigns the appropriate source and destination IP addresses. This information is called an IP packet. Then, the Ethernet protocol adds information to both ends of the IP packet, here and here. This is known as a data link frame. This frame is delivered to the nearest router along the path toward the web client. This router removes the Ethernet information, analyzes the IP packet, determines the best path for the packet, inserts the packet into a new frame and sends it to the next neighboring router towards the destination. Each router removes and adds new data link information before forwarding the packet. This data is now transported through the internet, which consists of media and intermediary devices. The client receives the data link frame that contains the data, and each protocol header is processed and then removed in the opposite order that it was added. The Ethernet information is processed and removed, followed by the IP protocol information, then the TCP information, and finally the HTTP information. So we can say we put the data in this way and then we read it this way. The web page information is then passed on to the client's web browser software. Here we have the functions on each TCP IP layer: the application, the transport, internet, and network access. Open standards guarantee that no single company product can monopolize the market. Standard organizations are important in maintaining an open internet with freely accessible specifications and protocols that can be implemented by any vendor. Standards organizations include the Internet Society, that is responsible for promoting open development, evolution, and internet use throughout the world. The Internet Architecture Board, that is responsible for the overall management and development of internet standards. The Internet Engineering Task Force, which mission is to develop, update, and maintain internet and TCP IP technologies. And the Institute of Electrical and Electronic Engineers, IEEE, that is the professional organizations that are dedicated to advancing technological innovation and creating standards. It creates and maintains standards affecting a wide range of industries, including power and energy, healthcare, telecommunications, and networking. Each IEEE standard consists of a working group responsible for creating and improving the standards. Here we have examples of working groups that exist in IEEE. Now we pass on to the reference models. A layered model, such as the TCP/IP model, is often used to help visualize the interaction between various protocols. A layered model depicts the operation of the protocols occurring within each layer, as well as the interaction of protocols with the layers above and below each layer. Benefits to using a layered model are that it assists in protocol design. Because protocols that operate at a specific layer have defined information that they act upon a defined interface to the layers above and below. It fosters competition because products from different vendors can work together. It also prevents technology or capability changes in one layer from affecting other layers above and below. It provides a common language to describe networking functions and capabilities. There are two basic types of networking models: the protocol model and the reference model. The protocol model closely matches the structure of a particular protocol suite. The TCP/IP model is a protocol model because it describes the functions that occur at each layer of protocols within the TCP/IP suite. Then we have a reference model. This model provides consistency within all types of network protocols and services by describing what has to be done at a particular layer, but not prescribing how it should be accomplished. The OSI model is the most widely known internetwork reference model. It is used for data network design, operation specifications, and troubleshooting. As shown in the figure, the TCP/IP and OSI models are the primary models used when discussing network functionality. Designers the 7-layer OSI model that has made major contributions to the development of other protocols and products for all types of networks. The OSI model provides an extensive list of functions and services that can occur at each layer. First, the physical layer protocols describe the mechanical, electrical, functional, and procedural means to activate, maintain, and deactivate physical connections for bit transmission to and from a network device. The data link layers protocols describe methods for exchanging data frames between the devices over a common media. The network layer provides services to exchange the individual pieces of data over the network between identified end devices. The transport layer defines services to segment, transfer, and reassemble the data for individual communications between the end devices. The session layer provides services to the presentation layer to reorganize its dialogue and to manage data exchange. The presentation layer provides for common representations of the data transferred between application layer services. And the application layer provides the means for end-to-end connectivity between individuals in the human network using data networks. The TCP/IP model for the internetwork communication is sometimes referred as to the Internet model. It defines 4 categories of functions that must occur for communication to be successful. Finally, we can compare the OSI model and the TCP/IP model. The OSI model is not as frequently used as the TCP/IP model, but it was an inspiration for many other models. As the network access layer, the TCP/IP protocol suite does not specify which protocols to use when transmitting over a physical medium. It only describes the handoff from the internet layer to the physical network protocols. Also, layers 1 and 2 discuss the necessary procedures to access the media and the physical means to send data over a network. As shown in the figure, the critical parallels between the two network models occur at layers 3 and 4. Also, layer 3, the network layer, is almost universally used to describe the range of processes that occur in all data networks to address and route messages through an internetwork. IP is a TCP/IP suite protocol that includes the functionality described at the OSI layer 3. Layer 4, the transport layer of the OSI model, describes general services and functions that provide order and reliable delivery of data between source and destination host. These functions include acknowledgement, error recovery, and sequencing. At this layer, the TCP/IP protocols, TCP and User Datagram Protocol, provide the necessary functionality. And finally, the TCP application layer includes a number of protocols that provide specific functionality to a variety of end-user applications. The OSI model layers 5, 6, and 7 are used as reference for application software developers and vendors to produce products that operate on networks.
A single communication, such as a music, video, or an email message, could be sent across a network from a source to a destination as one massive, uninterrupted stream of bits. If messages were actually transmitted, In this manner, it will mean that no other device will be able to send or receive messages on the same network while this data transfer was in progress. This large stream of data will result in significant delays. Further, if a link in the interconnected network infrastructure fails during the transmission, the complete message will be lost and have to be retransmitted in full. A better approach is to divide the data into smaller, more manageable pieces to send over the network. This division of the data stream into smaller pieces is called segmentation. Segmenting messages has two primary benefits. By sending smaller individual pieces from source to destination, many different conversations can be interleaved on the network. The process used to interleave the pieces of separate conversations together on the network is called multiplexing. Segmentation can increase the sureness of network communications. The separate pieces of each message need not travel the same pathway across the network from source to destination. The downside to using segmentation and multiplexing to transmit messages across a network is the level of complexity that is added to the process. In network communications, each segment of the message must go through a similar process to ensure that it gets to the correct destination and can be reassembled into the content of the original message, as shown in this picture. As application data is passed down the protocol stack on its way to be transmitted across the network media, various protocols add information to it at each level. This is commonly known as the encapsulation process. The form that a piece of data takes at any layer is called a protocol data unit (PDU). During encapsulation, each succeeding layer encapsulates the PDU that it receives from the layer above in accordance with the protocol being used. The PDUs are named according to the protocols of the TCP/IP suite. Data, the general term for the PDU used at the application layer. Segment, transport layer PDU. Packet, network layer PDU. Frame, data link layer PDU. And bits, a physical layer PDU used when physically transmitting data over the medium. Data encapsulation is the process that adds additional protocol header information to the data before transmission. When sending messages on a network, the protocol stack on a host operates from top to bottom. In the web server example, we can use the TCP/IP model to illustrate the process of sending an HTML web page to a client. The application layer protocol, HTTP, begins the process by delivering the HTML formatted web page data to the transport layer. Here, the application data is broken into TCP segments. Each TCP segment is given a label, called a header, containing information about which process running on the destination computer should receive the message. The transport layer encapsulates the web page HTML data within the segment and sends it to the Internet layer, where the IP protocol is implemented. Here, the entire TCP segment is encapsulated within an IP packet, which adds another label, called the IP header. The IP header contains source and destination host IP addresses, as well as information necessary to deliver the packet to its corresponding destination process. The IP packet is sent to the network access layer, where it is encapsulated within a frame, header, and trailer. Finally, the bits are encoded onto the media by the server network interface card. Encapsulation is reversed at the receiving host and is known as de-encapsulation. De-encapsulation is the process used by a receiving device to remove one or more of the protocol headers. The data is de-encapsulated as it moves up the stack toward the end-user application. Accessing local resources. OSI model describes the process of encoding, formatting, segmenting, and encapsulating data for transmission over the network. The network layer and data link layer are responsible for delivering the data from the source device or sender to the destination device or receiver. Protocols at both layers contain source and destination addresses, but their addresses have different purposes. Network layer. The network layer, or layer 3, logical address contains information required to deliver the IP packet from the source device to the destination device. A layer 3 IP address has two parts, the network prefix and the host part. The network prefix is used by routers to forward the packet to the proper network. The host part is used by the last router in the path to deliver the packet to the destination device. An IP packet contains two IP addresses. Source IP address, the IP address of the sending device. The destination IP address is the address of the receiving device. Data link address. The data link, or layer 2, delivers the data link frame from one network interface to another network interface on the same network. The IP packet is encapsulated into a data link frame to be delivered to the destination network. The source and destination data link addresses are AD. Source data link address is the physical address of the device that is sending the packet. The destination data link address is the physical address of the network interface of either the next hop router or the network interface of the destination device. To understand how communication is successful in the network, it is important to understand the roles of both the network layer addresses and the data link addresses when a device is communicating with another device on the same network. In this example, we have a client computer PC1 communicating with a file server FTP server on the same IP network. It should now be clear that to send data to another host on the same LAN, the source host must know both the physical and logical addresses of the destination host. Once this is known, it can create a frame and send it out on the network media. The source host can learn the destination IP address in a number of ways, but how does a host determine the Ethernet MAC address of another device? The sending host uses a protocol called Address Resolution Protocol, ARP, to discover the MAC address of any host on the same local network. The sending host sends an ARP request message to the entire LAN. The ARP request is a broadcast message. The ARP request contains the IP address of the destination device. Every device on the LAN examines the ARP request to see if it contains its own IP address. Only the device with the IP address contained in the ARP request responds with an ARP reply. The ARP reply includes the MAC address associated with the IP address in the ARP request. Accessing remote resources. The method that a host uses to send messages to a destination on a remote network differs from the way a host sends messages to a destination on the same local network. When a host needs to send a message to a remote network, it must use the router, also known as the default gateway. The default gateway is the IP address of an interface on a router on the same network as the sending host. It is important that the address of the default gateway be configured on each host on the local network. But what are the roles of the network layer address and the data link layer address when a device is communicating with a device on a remote network? In this example, we have a client computer PC1 communicating with a server named web server on a different IP network. IP addresses indicate the network and device addresses of the source and destination. When the sender of the packet is on a different network from the receiver, the source and destination IP addresses will represent hosts on different networks. This will be indicated by the network portion of the IP address of the destination host. The Ethernet data link frame cannot be sent directly to the destination host because the host is not directly reachable in the network of the sender. The Ethernet frame must be sent to another device known as the router or default gateway. In our example, the default gateway is R1. R1 has an interface and an IP address that is on the same network as PC1. This allows PC1 to reach the router directly. How does the sending device determine the MAC address of the router? All devices on the local network use the default gateway address to send messages to the router. After the host knows the default gateway IP address, it can use ARP to determine the MAC address of that default gateway. The MAC address of the default gateway is then placed in the frame. In summary, data networks are systems of end devices, intermediary devices, and the media connecting the devices. For communication to occur, these devices must know how to communicate and must comply with communication rules and protocols. TCP/IP is an example of a protocol suite. Most protocols are created by a standards organization such as the IATF or IEEE. The most widely used networking models are the OSI and TCP/IP models, associating the protocols that set the roles of data communications with the different layers of these models is useful in determining which devices and services are applied at specific points as data passes across LANs and WANs. Data that passes down the stack of the OSI model is segmented into pieces and encapsulated with addresses and other labels. The process is reversed as the pieces are de-encapsulated and passed up the destination protocol stack. The OSI model describes the processes of encoding, formatting, segmenting, and encapsulating data for transmission over the network. The Internet Protocol Suite is a suite of protocols required for transmitting and receiving information using the Internet. Protocol data units, PDUs, are named according to the protocols of the TCP/IP suite: data, segment, packet, frame, and bits. Finally, applying models allows individuals, companies, and trade associations to analyze current networks and plan the networks of the future. Thank you.